Right, so I'm just going to quickly go over the recitation packet from Friday for my OChem 2. This is for OChem 2 in the spring of 2025. And for the first part, actually, we redid this. The first 2 pages are a redo, so you can go look at Jessie's video for those. That is already linked in the OChem 2 practice problems, or she posted an announcement for it. But if you go down to Grignard reagents, this is where I'm gonna pick up. So if we are looking right here, the first thing that happens is the magnesium will insert itself in between the carbon and the bromine. And so if we redo that, so after we do that, we know that the Grignard reagent can sort of function as a salt. So really, instead of it being a covalent bond to magnesium, it functions more like MgBr+, and this carbon acts as like a carbon ion. And so then the negative part of the carbon will be attracted to the partial positive of this aldehyde, which is exactly what we've seen over and over with our reduction reactions. So I'm going to draw that. And if a new bond forms there, then this bond is going to break. And so we will get the, let's see if I can draw this way. I'm going to circle this lone pair that makes the new bond in pink, so that bond is right here. So the electrons right there are the electrons that make up this bond. And then I'm going to do the aldehyde in blue. So then we have the bond to the carbon to oxygen. It already had 2 electrons there. But when we take the electrons here in this bond, that broke and went and joined up here. So now this is negatively charged, and if you're not sure why, you can check out, I have at least a few videos on formal charge. And then this is also bonded to an ethyl group, and there's a hydrogen right here. You don't have to draw it in though because it's implied. So this is the first reaction mechanism, and then if you add water actually, H3O plus would be better, I think. But you can basically know that that acts as H plus, and you will get an alcohol. And you still have this and this. And I saw a lot of people drawing the curved arrow from the hydrogen to the negative charge, probably because we did a lot of work with hydrides being negative. But in this case, you always need to draw the arrow from the more negative thing. The way I remind people of that is like, negative people attack others, but positive people don't. So make sure that your negative is attacking, not your positive hydrogen here. Okay, so that's the first step. Next one, CH3, CH2. So this one already has the Grignard reagent. We don't have to make it. So we can just scratch that out and know that it acts like a carbon ion here. This will attack and kick up, and we get a benzene ring with O minus. And CH2, CH2, CH3, CH2, CH2, CH3. And that's our final product. If the second part, I guess I'll draw, is from the water, which really acid would be better if this was H3O plus. Should have done that instead. But so then we get our final product that looks like this. Water would also be fine, but I think acid is better because it will just neutralize everything, whereas water would just make a hydroxide ion, which is not great. So then this next one, we actually are going a step further, and we're going back to something we learned in OChem 1 in chapter 11, where we can convert an alcohol to a good leaving group with PBr3. And then we add the magnesium, so then that becomes a Grignard reagent. So we're generating a Grignard reagent from an alcohol. So then that acts like this, basically. It's just a lone pair, and on CO2, it would attack and break, and so you'd get a 5-membered ring with the carbon oxygen and then the O minus. And if you add acid to it, and the way, maybe I should draw the electrons of, I think this is a little bit harder to visualize. These electrons break and go up here, and so they joined that oxygen and made it negative. The other one on this side came from here. So that those two are the same, and just the other one is the one that broke. And then this carbon in the middle is this carbon right here. It's just not drawn in for CO2. There's no acid, actually. So technically, it would stop right here. But if we did have a step where we added acid, then it would become a carboxylic acid. But we don't have that step, so it's fine. Okay, so this type of question, this is retrosynthesis. And retrosynthesis actually, you should know the forward reaction really well to be able to get the backwards reaction. So you have to think about like what changed here, and then how could I recreate that change? So the first thing I'm seeing is this carbonyl group became alcohol. So we still have the bond to the carbon oxygen, but it's just a single bond to carbon oxygen, and this is gone. So I think something similar to a reduction reaction at least happened, where we have our O minus and our leaving group has left. You know, if we have our O minus, it comes back, it kicks this out. But we've only seen that with hydrogen. So I'm going to go through this I'm going to draw the reaction with hydrogen and see what we get. So if you have H minus and it attacks and kicks up, you will get O minus and H. And then this will come back down and kick out, and you will get an aldehyde. And then if we had another H minus and came back in and kicked up, you would get O minus and 2 hydrogens. And that's close to what we're looking for. But instead of 2 hydrogens here, we have 2 methyl groups there. So how could we get 2 methyl groups here? Well, we learned one way to get a carbon-carbon bond forming, and that is with a Grignard reagent. So if somehow I could have the nucleophile, instead of being hydrogen, be CH3, that would get me what I wanted. So instead of H minus attacking, we need CH3 minus attacking, and the only way to make CH3 minus is to have CH3 MgBr. I put that in weird, so let me rewrite it. MgBr. Oh, I'm running out of space. I'll do CH3 MgBr, and that's essentially CH3 minus. So if I have this as my nucleophile that attacks, then this reaction will work. And so that's how I process through this kind of thing. So the answer that I would put is CH3 MgBr would be my first step. And then to convert it to the alcohol, the second step would be H3O+. So this is what we call retrosynthesis. It's figuring out the reagents that we need to make the reaction happen. Okay, so the next one, I'm going to erase some of these, so hopefully you figured it out, and if you haven't, you can pause it and keep watching, since it's not like class where I go on and you're lost. You can pause these videos. Okay, so for this one, first thing I do is look and see what's changed. So this double bond is obviously gone, and we've added a carbon and then an alcohol here, and on this side we've just added a hydrogen. So the first thing I'm going to think is there a way to add something that's useful as a functional group right here? And the biggest thing I typically use that's like easy to convert is a halogen. So if you add a halogen there, a good way to do that is with HBr. So this is again a reaction that we learned in chapter 8, where we would get an H on one side, and then the other side it'll form a carbocation, and then the Br minus will come and attack, and you get a bromine right there. So that's our first step. But you might be looking at this thinking like, okay, so we can get a bromine there, but how do we turn a bromine into adding a carbon and an alcohol? And usually, if you want to add a carbon, that means you need to make a carbon-carbon bond, or we don't already have a carbon-carbon bond. And the one way that we've really learned to make carbon-carbon bonds is with Grignard reagent. So I'm going to think about turning this into a Grignard reagent. So we make this MgBr, that means it's basically just a nucleophile here. Okay, so I'm like, great, I can use this as a nucleophile, but what can it attack that will give me a carbon-oxygen bond? Well, if we have COH, that won't work with the Grignard because it would just deprotonate it, but what we have seen become primary alcohols are aldehydes. So if our Grignard attacks this aldehyde and kicks up, it will be O-, and then we'll have, oh wait, no, that's in the wrong spot. So I'm gonna circle this carbon. This carbon would be there, and then the alcohol would be here. It'd be O-, and then the two hydrogens are implied right there. So you don't have to draw those in. And then we would add acid. So the answer to this question, what I would put for my reagents would be 1, I would add HBr. 2, I would add magnesium in ether. 3, I would add formaldehyde. And then 4, I would add acid. So I would do it in that order. So a few things I guess I want to say on this. I saw one student who first added water across the double bond and made it like an alcohol. And then they did PBr3 or something like that, SOCl2, something like that. That is an option. And what I like about retrosynthesis is it's just like a puzzle. And you're just trying to figure out how would I make this happen. And that's different for each person. Every person will have a slightly different approach. So if you went about it a different way, but you ended up with something the same, that's totally fine. And so I guess I just want to encourage you that you don't have to do it exactly how I'm doing it, but make sure that you try things out. And if you're not sure, if you're like, I think this would work, say maybe you weren't sure that aldehyde would work, and so you just put R groups here, and then you tried it out, and then you're like, what do these R groups need to be? They should be hydrogens. That's fine. You can do a little bit of the forward reaction in order to get the reaction that you're looking for. So it's just a matter of thinking more carefully about, or not maybe more carefully, but thinking about like, what all do I need to accomplish this? And maybe thinking more creatively, thinking outside of the box and like trying things out. And this is something that I talk about a lot in Recitation is a lot of times students are like, oh, I don't know anything. And then they try something. I'm like, well, just tell me what your first thought is, even if it's wrong, who cares? And they try it and that thing is right oftentimes. And so if you're on the test or you're even trying to practice problems alone at home and you're not sure how to do something, just trying to see if the idea that you had works is a really good place to start. So I just want to encourage you in that. Okay, and then on the last page, or this last question, not last question, I guess second to last, it is the last page. This alcohol group shouldn't have been there, so you can just turn that into a carbon. I made a mistake. So when I'm looking at this, the first thing I'm seeing again is we start with a bromine and we turn it into an alcohol, but we didn't just turn it into an alcohol, we added 3 carbons. So this is probably going to be, again, a Grignard reagent. And that would mean that we would make it MgBr, which is essentially, oh, I always draw one too many. Oh, I shorted myself here. There should be this many carbons. So here we should have, and there's our lone pair. So the lone pair, again, that comes from between this bond right here. It's not really bonded to the magnesium. And this MgBr is positive. So we have our good carbanion. And so I need, again, a carbon with 2 CH3 groups, because that's what we have here, and a bond to an oxygen. But we know it's not alcohol. Something needs to attack there. And so I think it's going to look like this. So if that attacked and kicked up, what would I get? I would get carbon bonded to an O- and 2 CH3s. So these two electrons, these two blue electrons, made the bond right here. And then this, not that one, this carbon-oxygen bond is still in place. These CH3 bonds are still in place. And then these in this bond that broke are what made this lone pair right there. So that's how I'd approach that problem. So the first, to answer the question is, first you need to add magnesium in ether to make a Grignard reagent. And then the next thing you're going to do is add the ketone. This is actually acetone. And then the last thing you're going to do is add acid. Okay, there you go. Okay, and the last one, this is the epoxide reaction that we talked about at the very end of class. In general, if you have a Grignard reagent or any nucleophile, it'll attack right here and open the epoxide. So we get O minus and then the nucleophiles on this side. And then you add acid to make it an alcohol. Oh, that's another approach that might be helpful is oftentimes to do retrosynthesis, what people will do is, and this is probably a better way, and I probably should have shown you sooner, but I don't think of it that way, so it's hard for me to process it that way, is if you go backwards from here, so usually our last step to get an alcohol is protonate. So if you get O minus, how could we have gotten an O minus? Well, probably it started as a epoxide and whatever, I guess, so this is where it's hard for me to think of, is started as an epoxide. That's where we get the 1, 2 carbon and the oxygen. But then where did this thing come from? Your nucleophile must have come and attacked and broke it open to get to the epoxide. So then that's how we get back to our starting material, and we can tell what our nucleophile is just by looking at this. So our nucleophile is CH3 minus, because CH3 minus had to have been the thing that attacked to get right there. So CH3 minus must have been our nucleophile, so we must have MgBr. I always want to put it on the wrong side. CH3 MgBr. So we must have started with CH3Br and added magnesium. And I should have put that above or below there. Added magnesium in ether as our first step, and then added all of this to this reaction. So this would be our first reagent, and our second would be H3O+. So this is kind of different because you didn't start with the reagent that would be your Grignard, unlike the other two before that. So retrosynthesis, I mean, you can kind of, I guess, think about what makes the most sense to you. If you like to think about going backwards from your final material, I like to think about how I like solve a puzzle, like how can I take this and end up here, almost like going through a maze. But before you can do retrosynthesis well, you should be able to do the forward reactions pretty well. So that should be the last thing you worry about when you're doing reactions. All right. Well, I hope this was helpful to y'all, and I'll see you in class on Monday.